Lovely. So my name's Gareth Kitchen. I'm a clinical lecturer at the University of Manchester and a consultant anaesthetist at Manchester Royal Infirmary. Throughout the last couple of years, I've been on an NIHR Development and Skills Award, placed with Tony Bashall at Zenzium, where I've spent time gaining skills working at the interface of industry, academia and the NHS. The projects we worked on were based on wearable technology. This included continuous vital signs monitoring in the hospital, as well as consumer wearable devices in patients in the perioperative period. We've also collaborated with the Alliance Business School in the Data Visualization Observatory, funded by Translation Manchester, to work on explainability using visualization of AI. Skills have recently allowed me to be successful in gaining $2.5 million from the NIHR to do a clinical effectiveness trial in a medical device. And that's where my relationship from Tony, our speaker, comes from. But before I introduce the speaker, a couple of announcements, housekeeping. We're going to record the talk, as I've already said. Please keep your microphone on mute during the presentation. We'll have a Q&A session at the end. If you want to write your questions throughout the talk, I'll keep a note of them, try and put them into some logical order. And after the webinar, we'll ask you to fill in a short survey. It's really useful so that we can make better use of this time and take your feedback to the future sessions. So it's a real pleasure to introduce Tony Bashall, Managing Director of Zenzium Ltd, and he's going to talk on high definition healthcare observations, a paradigm shift. Welcome, Tony.
Thanks, Gareth. Good afternoon, everybody, and I'd like to thank the organisers for inviting me to give this presentation. As Gareth says, we're going to be focused on talking about high definition observations. And Zenzium is focused on AI. It's focused on AI specifically around time series data. So that's how the connection is made between using time series data, continuous monitoring. How do we get that continuous monitoring? We use wearables and then apply the data to the AI to be able to discover onset of conditions, etc., which we'll talk a little bit about. So just before I start, I'll just briefly go over, we're in a number of collaborations with MFT, Christie's, University of Manchester, and you can see the logos there on the bottom. A lot of those are in ongoing, actually, and they're on clinicaltrials.gov. So if anybody wants any of that information, just shoot me an email at the end and I can forward a link over. So what landscape are we looking at? We're kind of looking at the whole continuum between wellness and health or disease. And generally speaking, most people, probably 80% of the people who consider themselves well are actually in that middle comfort zone. So that's the neutral zone. So they have no symptoms. The nutrition is inconsistent. They exercise sporadically, and health is not necessarily number one priority. So if we move that towards the right, we improve the wellness. And if we move it towards the left, we improve the disease, unfortunately. So it's a continuum, and we need to think about where we're sitting. And one of the things which is happening at the moment within the healthcare industry, wellness industry worldwide, is the line between wellness and healthcare is beginning to blur. And that blurring is driven by a number of factors, and we'll talk about that. But a lot of those factors are paradigm shifts. And those paradigm shifts have really been brought on by the pandemic, by COVID. So it's kind of catalyzed the adoption of some of the newer technologies. It's certainly made people more aware of wellness. And we now even see some of the wellness philosophy being actually used within healthcare. So health is not necessarily the absence of disease. So as we've said, you know, that comfort zone in the middle is a nice area to think you're in, but really we need to move it further to the right. So a number of things need to happen to make this possible. And these are kind of prerequisites. The prerequisites are usually around the data. So obviously we're using AI, we're taking continuous monitoring. What that means is we acquire a lot of data, and that data is acquired in a time series manner. So it kind of necessitates moving to a cloud-based infrastructure just so we can get the information into a database in near real time or consistently across multiple locations. The other thing which is really important is the analog to digital measurements. We're still in a little bit of the analog era, so we still write down things like blood pressure, body temperature on a piece of paper. We then transcribe that via a computer into electronic health record system or something like that. And what's really changing and is being adopted very quickly is the movement to take that digital information direct from the measuring device straight into the electronic healthcare record systems. Data silos are beginning to disappear, and we're talking about data fusion. So we've got multiple databases. Usually we've got electronic healthcare record systems, we've got labs, we've got vital signs, we've got observations, we've got patient records, and all of that is moving towards data fusion. Interesting aside here is that a number of years ago, the House of Lords Select Committee on AI identified the NHS as a key strategic resource for the UK, purely because of all the data that we have, all the data that's been generated in all the different trusts. But one thing which is missing is how do we fuse that all together? And that's an ongoing process. If we share data, we've got to make sure it's secure. So that's another thing which is happening, is a prerequisite, has to happen. Secure data environments have been established, research environments where we can look at research data across NHS trusts, across NHS to private companies, across institutions, academia, etc. So that's really been something which is happening very quickly. And then, as far as the processing of the data is concerned, we're definitely moving from a statistical view to a machine learning view, and we'll see a little bit about what that means. And that necessitates moving from algorithms to models. And again, we'll talk a little bit about that. One of the key things which is missing is what's on the right-hand side here, is we need to think about what question we're trying to answer. And then once we've decided what the question is, it's really important to have a structure and a process behind it so we can agree, iterate, go backwards and forwards with the data. So this is a data science toolkit that we're introducing and we're using. And it really is like a scrum with software engineering, if anybody's familiar with that. It's a process by which you do frequent meetings, you exchange data, and you look at what you need to do to get the outcomes. In terms of the paradigm shifts, which are not necessarily prerequisites, but they are happening, and these are really happening, as we said, as a consequence of COVID and the pandemic, which amplified all of these shifts. We're moving from episodic to continuous measurements. So episodic measurements are things like you go to the doctor, your weight's measured, you check your blood pressure, you check your heart rate or your body temperature. You're not continuously looking at those, although you can, but generally speaking, we get most information and most resolution of that information if we continuously measure things. To put it in context, if you think of a Formula One race car has 300 sensors. It's streaming data continuously into a database, so you can look at future events, you can look at optimizing things as they occur. We've got jet engines, which are doing predictive maintenance, continuously sending information from a multitude of sensors. The question is, why are we not doing that with people? Why are we not taking all of this information continuously, putting it in a database to improve outcomes by using things like AI? We're moving definitely from location to remote monitoring. RPM is remote patient monitoring, and that was really driven by COVID. This can be episodic, but it can also be continuous as well. The other thing which is really changing is we're moving from a clinical perspective to a real-world evidence perspective. So now the FDA and other regulatory authorities are allowing clinical trials to look at devices which are non-medical, for example, and to generate real-world evidence in concert with clinical to put into the process. We're definitely moving from reactionary to proactive. One of the big areas we're focusing on with MFT and the University of Manchester is prehabilitation. What can we do to individuals prior to an intervention so that that intervention can be more successful and the outcomes are better? So that's applying a lot of this measurement, continuous view into what's going on before you actually begin to intervene. Generally, we're moving from health to wellness, moving from medical devices to consumer devices, and that has a knock-on effect in terms of now we think of absolute values, body temperature, blood pressure. Probably what's more important is the trend associated with that. So again, we're now looking at the continuous measurement to generate trends. What was your blood pressure yesterday versus today? Not that it's X or Y. And that's also changing paradigm for patients. Patients are no longer patients, they're individuals. And definitely in the United States, things are now moving towards members. So you are a member of a healthcare organization. You're not a patient. So that changes the perspective and it puts the onus a little bit on the individual to do self-care. So those paradigm shifts are taking place, sometimes more than others. But what are we trying to do? We're trying to get this information. So this information can either be very deep, in other words, it's got a lot of fidelity, it's got a lot of resolution in it, or it can be very broad, where we may be monitoring just one or two things. And those one or two things are important, but they are not taken in isolation. So if you look at the top left here, you can see images and HRV. These are two big areas where the information contained is very, very rich. Images, for example, Moorfields and UCL released a paper in September last year showing that you can take OCT, optical coherence tomography images from patients' eyes, and then to be able to predict things in the future, not necessarily around the eye, but myocardial infarction, heart disease, Parkinson, and the list goes on. So that's a very rich data set. And we're doing the same with HRV. HRV stands for heart rate variability. And that's a statistical measure. In actual fact, what we're doing is taking interbeat intervals or RR intervals. That's the measurement of time between the heartbeats, and applying a number of different algorithms, either time domain, frequency domain, or nonlinear. And now we're using deep learning. And we're getting, hundreds of features just from that one measurement. So it's very, very rich. And then across the other side towards the right, we have more singular measurements, which are still important. But what focused our search for something like HRV was some of the COPD work we did. So COPD, we did 6 different devices that patients had to use every day. They're measured with a spirometer FEV1, blood pressure, weight, heart rate, activity, sleep, temperature. And those were singular devices, which just put a burden on the individual to measure those every single day. So what do? We look for one device which potentially could replace all of those. And we found one which uses heart rate variability and activity. It's a watch or a polar chest strap or something like that. And we'll talk about the options as we talk about the devices. However, statistically, the ability to predict an onset of an exacerbation was exactly the same given one device or 6 devices. And that was driven by the richness of that heart rate variability data. So we can think of very scalable things on the left-hand side at the top, and bottom right is context dependent. It's interesting to note that if we look at those images in HRV, and I think probably there will be others in the future, it's very much driven by measuring things in the autonomic nervous system. So we're looking at the parasympathetic or the sympathetic nervous system to be able to extract all this data. And things like, Parkinson's disease, Alzheimer's, COPD, pain, stress, they're all dependent upon some interplay of the autonomic nervous system. So it makes sense that we can extract all that data and make sense of it. In terms of the journey, a patient or an individual or a member can say, I have these symptoms, and those symptoms are conditions, depression, performance, or chronic pain. Associated with that is an emotion. Maybe they're sad, maybe they're angry, and then associated with that are the feelings behind it. They're stressed, they're tired, they're in pain. So those are very qualitative measurements. And what we're focusing on using is the biomarkers below, which are very quantitative. So we got molecular, histological, images, and physiological. And you can see those individual metrics are very quantitative. They are measuring values, and those values are changing, and those values are changing as the disease progresses or it improves. And across that spectrum at the bottom, we're moving from screening to risk to diagnostics, prognostics, predictive response to therapy, monitoring, and safety. So biomarkers are usually associated with that diagnostic criteria. Can we see something which indicates what the disease or condition is? And what's happening quite rapidly, actually, is there is a movement towards using better biomarkers. And these better biomarkers are both good and bad. They're good in terms of the specificity and the selectivity for a given condition or disease, but they're not generalizable. So, for example, we wouldn't use some of them for inflammation if we were trying to assess pain. We wouldn't use fibromyalgia for anxiety. So they're very much in their own boxes. They're very specific and selective, which is good for identifying those conditions. But what that means is that once those biomarkers have appeared, it's like having a rain gauge and saying there's water in the rain gauge, therefore it rained. Yeah, it's obvious it rained because there's water there, but it's too late. It has no predictive capability whatsoever in terms of detecting onset of disease. If you have a high PSA or a high CA-125, then it probably means you have prostate cancer or ovarian cancer. They're not indicative. And the same can be relayed around the molecular things about cholesterol, glucose. And then some of the physiological things as well. Again, you know, if you have a fever, you have a high temperature. Well, you have a high temperature because you have a fever. It's got no predictive capability that you're going to generate a fever in the next 2 or 3 days. So that's where AI comes in, and that's where our focus and what we've been working with MFT and the University of Manchester on is all about. It's how do we predict the onset of these things? And if we look here, for example, this is a onset of COVID. So this was a patient. This is 5 different time series data streams. And we can see that there is a pattern emerging in the event. And you can see that, you know, the first feature goes down, the second goes down and up, and so on and so forth. So that is indicating something's happened, and we call that a digital biomarker. And that digital biomarker is a digital way of saying that patient has COVID, for example. But it doesn't do anything, again, for our prediction. So what we need to do is to take the data prior to the onset of that digital biomarker, put that in a deep learning algorithm, for example, and then we can work out when is that digital biomarker going to occur. So it's important that when we look at what we're measuring for the digital biomarker, it's the same as we're using to identify the event as we're saying we're using to predict the event. So this is a 3-day predictive algorithm that is saying you've got an 87% accuracy if this occurs, that you're going to develop COVID in 3 days. So that gives you an idea of the flavor of what we're doing. It may not be the onset of a disease. It may be transfer from a ward to an ICU. It may be an outcome. It may be improvement rather than deterioration as well. So we're taking these time series data streams before the digital biomarker, and we're able to predict the onset of that. If you look at the features, and in AI, we call these individual measurements features, and you can see that we've got a whole plethora of things. Some of them are actually biomarkers, some of them are measurements, other them are characteristics. So, you know, weather, seasonal changes, environmental, air quality also play a role here. And those are driving things like epigenetics and onset of disease, and there may be causative or correlative anyway. So if we then shake this up and put it in our buckets, we end up with really demographic data, episodic data, longitudinal data, and time series data. So if we take some of the left-hand end of the spectrum, you know, those are things that happen once: the gender, the height, the weight, the age. We usually measure those, and they're pretty fixed. I mean, they may change over years, but that's another story. What we can use there is clustering to identify which patients cluster together, and then we can drive that clustering based on what we're looking at in the time series. So episodic is a single measurement, usually, you know, once a year, once a month, whatever. Longitudinal is more frequent, so it can be time series, but it's not as time series as what we really refer to as time series measurements. For example, HRV, where we're getting these 45 to 100 features, we're taking every heartbeat. So it's 2, 3, 500 milliseconds. There's a data point. So it's a lot of data. From that, we're able to apply deep learning and traditional statistical algorithms to actually identify onset of disease or conditions. So how do we get all this data? Well, we have to use a wearable. And the wearables really delineate into two areas. They are medically approved or they are consumer related. And the first list there is more consumer related. And we use things like the Oura Ring, the Withings watch, the Polar chest strap, the Garmin watch, Corsano, the Apple Watch, Mendy, Muse bands, and the Whoop band. So those are all generating data continuously. And the diagram there shows what type of data we're generating. So things like heart rate, RR intervals, breathing rate, activity, sleep, ECG, oxygen saturation, conductance measurements, core body temperature. All of those are taken in a time series manner, sometimes in near real time, and those are put into our database, and then we begin to look at that, what that means, and can we tease out of there some predictive capabilities. The ones at the bottom are more medical devices, things like Philips patient monitoring, MediBiosense, which is a patch, the Hexoskin, Masimo, which is deployed in a lot of hospitals, and Isantis is another patch as well. So we have to really think about what accuracy do we want to achieve? Do we want that accuracy over a trend, or do we want the trend to identify anomalies? So depending upon the answer to those questions will depend on which device we use. Interesting development actually the weekend was the Google phone will now has a temperature sensor on there, which is approved by the FDA. So it's the first temperature sensor in a phone that you can measure your temperature with. So again, that's episodic. You're not going to hold the phone in front of your head forever. But if you don't feel well, you can use that to assess your temperature. So the boundary between medical devices and consumer devices is blurring. And you see that with things like the Apple Watch or Corsano. They have AFib detection, which is approved by the FDA, but other bits of the watch are not. Generally speaking, I think everything is probably going to move towards being regulatory compliant. So once we've got all of this stuff, we predict onset of disease. What do we do about it? So we have to intervene somehow. And the intervention can either be on the healthcare side or it can be on the wellness side. And you can see on the healthcare side, we're talking about, proton beam therapy, radiotherapy, surgery, pretty invasive. Non-invasive is more medications, therapeutic, nutrition-based. And then on the non-invasive wellness side, there's a movement towards applying a lot of these techniques like mindfulness, meditation, relaxation. And one of the probably flag bearers in that is Harvard Medical School. The Mind Body Institute now prescribes mindfulness, meditation, and relaxation as the first go-to for hypertension. If that doesn't work, then they give the drugs. So again, this is a paradigm shift and things are blurring. Things are moving from the wellness side to the healthcare, and obviously from the healthcare to the wellness side as well. So after we've, decided which intervention to use, we need to test that intervention is effective. So first of all, we're doing identification of the digital biomarker. Then we assess it, we subject the individual to a therapy, and then do an assessment of what that therapy is doing. So again, we're looking at using these things, the digital biomarkers, which again, are like the rain gauge. It's too late. Digital biomarker says, you've got this condition. Let's do an intervention and see if it improves it. But what if we could apply AI, and that's what we're doing, and we're doing predictive digital biomarkers. So this occurs before usually the patient or individual is symptomatic, they're asymptomatic, and we can intervene with some therapy to better improve their outcome. And again, a lot of these are moving wellness-based as well as healthcare-based interventions. So the current activities we're looking at are using these devices. Currently, we're looking at, we've actually finished the COSMIC-19 study, which was with MFT. This was looking at patients admitted during COVID to see if we could predict when those patients needed transferring to the ICU. If you transfer a patient to an ICU before they need to be, then the outcomes have been shown to improve. So that's in the process of being written up at the moment, and that'll be peer-reviewed and published in the foreseeable future. Embrace is looking at oncology. We're looking at colorectal, lung, and using a CAR T therapy as an intervention, and then looking at proton beam therapy as well. And we want to see is there an improvement with outcomes? Can we associate specific patients with improved outcomes? And then Kidneys for Life is really about that prehabilitation. These are live donors, so people are donating their kidneys for a recipient, and we do something to the donor or the recipient prior to the intervention, the transplant, that improves their outcome. And this is the whole area of prehabilitation. If we improve their sleep, if we improve their activity, if we improve a number of different metrics, does that have an impact on the outcome? Interesting area with the NHS staff. Can we look at sleep, stress, and vitals to predict, anxiety, burnout, effects of shift work, things like that? And that's an investigational study which is underway. And then the other things we're looking at are pain, stress, and fatigue. Again, continuous vital signs. We're trying to identify that digital biomarker, which then moves on to, can we look at a predictive digital biomarker? A lot of activity we have done in the past on stroke, looking at heart rate variability. Can we predict or show which patients are going to improve their aphasia? And again, that's actually been published. An exciting area which we're just embarking on is mental health. Depression, anxiety, schizophrenia, you mention it, they all impact that autonomic nervous system, that parasympathetic, sympathetic balance. So it's ideal for using things like heart rate variability, which we're looking at to try and predict which patients are more subjective to developing those conditions, and potentially which interventions do we use. So what's AI all about? It's really about one thing. It's about prediction. So we think it's intelligent, we think it's thinking about things, we think it's developing ideas. It isn't. All it's doing is predicting. So I'm sure everybody is aware of ChatGPT and what that is doing. ChatGPT is just predicting the next word in a sequence, or the next sentence in a paragraph, or the next paragraph in a page. It's all about prediction. But one of the things you have to do with AI is you have to identify the problem you're trying to solve and what question are you trying to answer at the beginning. So that goes back to that circular animation where we look at, what are we trying to do? What are we going to use the data for? And that's all driven around answering these two questions. So prediction is very AI-centric. Will AI replace doctors, nurses, healthcare professionals? Probably not, because the component it's missing is judgment. So judgment is a very human characteristic. Prediction is a very mechanical AI process. And if you put the two together, that's ideal for making a decision. So prediction plus judgment gives you a decision. And as Gareth mentioned at the beginning, we're looking at a research project with Translation Manchester to actually describe why that decision has been made. We're looking at trying to have explainability in the models. And how do we explain why it's made this prediction? Then how do we look at the judgment? And is that decision the correct decision? So the approach of handling the data is very different. A statistical approach, we've got the data, we've got our algorithm, logic that goes into our mechanical process, and out of it comes an answer. So that could be means, it could be averages, it could be all whole range of statistical metrics. AI is doing something totally different in as much that we're still putting the data in. That's all that time series data. We're putting the answer in, and the answer in this context is the ground truth. This patient developed an exacerbation. This patient was admitted to the ICU. This patient developed COVID. And out of the other end comes the logic. And the logic is not an algorithm anymore, it's a model. So that model is trained on that answer and the data going into that processing capability. So that output can be a classification or it can be a regression. So, did this happen? Did that happen? Or what's the value of this? What's the value of that? So that whole process is undergoing dramatic change at the moment. The general statistical migration to AI and machine learning. This is a very exciting area which is developing. Everybody's familiar with large language models, ChatGPT. These are known as foundational models. Why are they foundational? Because they are scalable and they're generalizable. So generalizable is good in terms of applying it to a lot of different conditions and onsets. So Moorfields in September had the RET-FOUND foundational model. That's using OTC scans. They've got 1.6 million OTC scans, and they're predicting onset of conditions, not necessarily related to the eye. And we talked about that at the top left of that graph that we looked at. And again, what we're trying to do is to develop deep HRV as a foundational model, again, for looking at various diseases. So this is 180 degrees away from those better biomarkers. Better biomarkers, yes, I have this specific disease. It's very identifiable. It's very specific. Whereas what we're trying to do here with the foundational models is to have a model which can look at all the diseases and predict which one is likely to occur. So the difference is scalable, generalizable versus specific with the other biomarkers. So RET-FOUND was published, as I say, in September. It has got a lot of future potential. And we're just at the beginning of embarking on the development research really at this stage to develop that deep HRV as a foundational model. So that gives you some idea and perspective of what we're looking at across the spectrum. We're getting higher resolution data, which is more specific, more measurable. We're acquiring that on a continuous basis. We're taking wearable data to generate that continuous data stream, and then putting that data stream into machine learning and AI to begin to make our predictions. Very interestingly, this is a translation meeting. It's only less than 2% of the research and papers that have been using AI or machine learning in the medical domain actually get implemented. So we need to think about how we can speed that up. And I think one of the reasons is those paradigm shifts. It's, one paradigm shift is not going to do it. We've got to have multiple paradigm shifts. We've got to have those prerequisites also in place before we begin to acquire the data. So, I think the future looks very rosy. I think it's advancing very quickly. But as far as the implementation, I think it is a little slower than we need, particularly if you think of Formula One race cars. They've been taking 200 sensors now for years, data streams, and looking at how that car is performing. Just leave you with the thought, what can we do to make that happen on ourselves? Okay, thank you.